Okay, today we're going to start our new chapter, chapter 14, and we actually do a shift in physics up to the late 1800s, covers everything that we've covered so far in physics 20 and 30. So all of Newton's formulas and motion, acceleration, gravity, circular motion, all that kind of stuff, plus what we did in 20 and 30 on waves and EMR, electricity, magnetism. Thomson did some work on figuring out what the masses of electrons, protons, all that kind of stuff is. So all of that stuff is considered classical physics. It's good, it all works, but it presents some problems when we get into some newer topics. The first topic we're going to look at that classical physics can't explain is called black body radiation. And what black body radiation is, think of it as a black body as just being an object that can absorb all of the electromagnetic radiation that it strikes, or that strikes on it. So kind of think of it like being an empty box. So if you have this empty box and we shine light on it, the box, think of the box as being open, it's going to absorb all of the light and the box will close. And what happens is, it doesn't matter what the radiation is. So if we shine light, radio waves, microwaves, ultraviolet, cosmic, a black body will absorb it all perfectly. And the reason we call it black body, it's kind of like the color black. The color black basically is the absorption of all light. We don't see any light reflect, so that's why we see black, or the absence of light. So kind of using that same idea, it's just saying a black body absorbs everything, not just light, but all EMR. And we know that electromagnetic radiation, the higher the level of frequency, the higher the energy. So really what's happening is the black body is absorbing energy. Then, if we heat it up, so a black body will absorb energy at cool temperatures, and it'll then re-emit it when it gets heated, and it'll release that energy then as EMR once again. So according to classical physics, is the more energy that gets absorbed, the more it should get released. So the higher the frequency, the higher the energy, the more that's going to get released. So using common sense, we should be getting sort of a graph that would look linear. We should get bigger and bigger as the frequencies get higher and higher. So what happened when they actually tried this is it didn't work out. So the higher the frequency, we think the higher the intensity. So it should look like the red line. But in reality, they actually got it that it was pretty linear for a point, and then it sort of hits sort of a threshold, and then came crashing down. So what happened is when they were doing this experiment, they actually found out that the frequency that it crashed at was about UV. So radio waves and up, once we hit visible light and all that, we started to fall apart, and we hit UV, it crashed, and then when we got towards gamma, it definitely didn't follow the pattern that we thought. So this black body caused a perplexing issue for a lot of scientists. So the best minds around at the time couldn't figure out why. All they knew is that when it hit UV, it sort of crashed, so they called it the ultraviolet catastrophe. There was no explanation for it. They just had trouble figuring it out. So when they did different experiments, they found that that peak, or that part where it crashed, just changed as you change frequency. So if we had more intense, it would just shift that thing one way or the other. So, and if we actually increase the temperature, so the higher the temperature, the higher the frequency, but if we also increase the temperature, we actually get a visible shift in color, so from the red end of the spectrum towards the violet end. So that's why when you have a fire, you turn on your electric element on your stove and it gets hotter and hotter, it gets brighter and brighter red, or, it's kind of turns to almost a yellowy sort of color. Or if you think of a campfire, once it's burning, it kind of starts reddish, goes to a yellow, and eventually it might even get to a blue sort of color, or even white hot. Like it might get hot enough where it actually just kind of looks like a white glow off of it. So it kind of explains why we get that. So as it hits certain temperatures, we get a certain level. So Max Planck was the first guy. He was in the early 1900s. What he did was he figured out sort of an explanation for this. He said the reason why we're getting these thresholds is that we think that as we add more and more energy, the electrons are just going to take that energy and start vibrating faster and faster. But what he said is, instead of it being sort of a straight curve like that, what happens is we have to get to certain levels. So the electrons have to take a certain amount, so it stays sort of flat, and then they're going to jump up to the next level. Then it's going to take more energy, more and more and more. Eventually it'll hit enough and it'll jump up to the next level. So he said, think of it as sort of like being stairs, or where we got to go up in increments instead of it just being a continuous line. So we need these minimum amounts in order to make it jump. So he called these levels or these amounts a quantum. So a quantum is, just think of it as a small bundle or a small piece of energy. So the idea is that if we have these bundles or pieces, that's going to explain why we're getting black body radiation and things like that. So his formula that he used is pretty simple, just E equals hf. So our energy equals h, so his constant, times whatever the frequency of the EMR is. So Planck's constant is 6.63 to the negative 34. But remember, we can change from joules to electron volts just by dividing by 1.6 to the negative 19. So if we do that, we can actually get Planck's constant as 4.14 to the negative 15 in electron volts. So it just depends whichever way the question is given to you, pick one or the other. And also this, remember, this is for one quantum. So if we just have one quantum of energy, that's how we're going to use E equals hf. So obviously if we have more than one, if we had 2, we'd double it. Or if we have 10, we times it by 10, and so on. Okay, so that's the key thing idea. Think of energy as not being continuous. It's actually bundles or little amounts. So kind of like when you look at a picture, we think of it on the big picture, we just see the entire picture. But if we look close, we see a whole bunch of dots that the printer makes that makes up the picture. So it's sort of the same thing. He's saying EMR is like these whole bunch of bundles that once they're all together, that's what makes what we see, the light or the radiation or whatever it is. So let's go through a couple of formulas, or a couple examples using his formula. So the first one is, it's asking what's the smallest amount. So the smallest amount would be for one quantum. So all we have to do is go E equals hf. So our h is 6.63 to the negative 34, times it by our frequency, 4.5 to the 14. Multiply those together, and we get an answer of 2.98 to the negative 19 joules. Okay, so if we would do this with joules, for the h constant, we get 2.98. If we would have done it with the electron volts, then our answer would be in electron volts. So it doesn't matter which one you do, it's just one or the other. And you can always convert back and forth just by dividing by 1.6 to the negative 19. Okay, so let's do another one. So this one says, what's the minimum energy to get 212 nanometer wavelength? So we know that E equals hf, but we also know from an earlier formula that velocity equals frequency times wavelength. And we know velocity is just the speed of light. So we can actually determine that frequency then is speed of light divided by wavelength. So that's how we're going to do this one. We're going to go hc over lambda instead. And because we have electron volts, let's use the other h. So 4.14 to the negative 15 times it by speed of light divided by our wavelength of 212 to the negative 9. And we crunch all that out, we get 5.86 electron volts. So if you use the h in electron volts, your answer will be electron volts. If you use the h in joules, you'll get an answer of joules like we did for example 1. The last little bit for this stuff is Albert Einstein came along after Planck and went one step further. Planck sort of basically, he was using the idea of quantum, black bodies, energy of EMR. So what Einstein said, well, because light, visible light, is a section of EMR, then it should apply to light as well. And if that's the case, that means light is actually made up of individual particles, not as one solid wave that we've been dealing with. So if you think back to the start of the last unit, we said that the early guys like Newton thought light was particles. The later guys like Huygens and Thomas Young, they figured out that light had to be waves because it was refracting and diffracting and all those kind of things. So Einstein now is actually going around back to 360 saying, well, maybe light's actually a particle. If it is working like quantums, then it's actually a particle. And Einstein called those particles of light a photon. And then he said, well, if light is made up of photons, then it has to be a particle. Obviously, the science world didn't like that idea because they've just finished coming up to the conclusion that it was a wave. But since his time, we've now said that we think of light actually as being a wave, but it's little particles that travel in a wave pattern. So we think of light as being photons or particles, and they travel from one place to the other as a wave. So it's kind of a combination of the two ideas. So So this last example is, let's calculate how many photons are in that light wave in a laser. So if we have a laser, it says its frequency is 4.38, so we can calculate its energy. So let's go E equals HF. So we'd have 6.63 to the 34, times that by our frequency, 4.38 to the 15, and that gives us an answer of 2.9 times 10 to the negative 18. So that's joules. So that's how much energy one photon has. So now the next question is then, it's asking how many photons would you get per second. So the trick to this one is they tell us that the laser gives off a power of 4.06. Remember, power is in watts, and which is just energy per time, so that would be a joules per second. So what we want to do then is take this 4.06, so 4.06 milliwatts, so that'd be 4.06 times 10 to the negative 3. Think of that as joules per second. And we're going to divide that as 2.9 to the negative 18 of joules per photon. Right? That's how much energy one photon had. So now if we divide these, we divide the numbers, we get 1.4 times 10 to the 15. And you can see we get joules divided by joules, so those cancel. And if you think of fractions, when you flip it around, you'd actually have photons on top and seconds on the bottom. So for this question then, that means that little laser is emitting 1.4 times 10 to the 15 photons per second. So that's why we don't see light as particles. It's happening so fast. These photons are coming at such a fast rate, it looks like it's just a solid, continuous light source. But in reality, they're small bundles being emitted every at a certain frequency, and they're following a wave pattern. So that's kind of where we've come with this now, is we've taken light as a wave, but now we're breaking it up individually into a bunch of photons that are being emitted. And that's all.